Beyond the familiar boundaries of our cosmic neighborhood, where sunlight fades to a mere whisper, lurks a cobalt giant shrouded in mystery. This is Neptune, the eighth planet from our sun, a world so distant that it remained completely unknown to humanity until just 179 years ago. Yet despite its remoteness, this azure behemoth harbors some of the most extreme and bizarre phenomena ever discovered in our solar system. What you're about to discover is not merely another planetary profile, but a journey into one of the most enigmatic worlds in our cosmic backyard, a planet discovered not through observation, but through the power of mathematics, a world with winds that exceed Mach 1.5, and an interior where diamonds may literally rain from the sky. This is Neptune, guardian of the outer solar system, and keeper of secrets we've only begun to unravel. Our voyage will take you from the planet's revolutionary discovery that transformed astronomy forever to the cutting-edge research that's revealing Neptune's deepest mysteries. By the end, you'll understand why this distant ice giant, despite being the solar system's least visited major planet, may hold the keys to understanding thousands of similar worlds now being discovered around other stars. What cosmic revelations might be waiting in Neptune's azure depths? What secrets could this distant sentinel reveal about our own origins? And how might this mysterious world change our understanding of the universe itself? Join me as we voyage to the very edge of our solar system to find out. The mathematical miracle, how Neptune was discovered without being seen. The discovery of Neptune stands as one of the most profound intellectual achievements in human history, a moment when the power of mathematics and the human mind triumphed over the limitations of our senses. Unlike every other planet discovered before it, Neptune wasn't found by simply looking up at the night sky or sweeping telescopes across the heavens. Instead, it was predicted through the elegance of mathematical equations and the laws of gravity before anyone had ever seen it. The story begins in the early 19th century when astronomers noticed something peculiar about Uranus, the seventh planet from the Sun. Its orbit wasn't behaving as it should, deviating slightly from where calculations predicted it should be. These tiny discrepancies, mere fractions of an arcsecond, suggested an extraordinary possibility. An unknown world beyond Uranus was gravitationally tugging on it. In a remarkable case of scientific parallel thinking, two mathematicians, working completely independently, took up this challenge. In England, John Couch Adams, just 24 years old and fresh from university, began calculating the position of this hypothetical planet in 1843. Meanwhile in France, Urbain Le Verrier embarked on the same mathematical quest. Using nothing but Newton's laws of motion and the observed irregularities in Uranus's orbit, these brilliant minds calculated where this unseen world must be. The precision required was staggering. They were attempting to locate a tiny speck among billions of stars based solely on minute wobbles in Uranus's path. The culmination came on September 23, 1846, when astronomer Johann Galle at the Berlin Observatory pointed his telescope to the exact spot Le Verrier had calculated. There, just 1 degree from the predicted position, was Neptune, a new world revealed not by chance, but by the predictive power of science. Within an hour of beginning his search, Galle declared, "That star is not on the map." In that moment, our solar system expanded, and humanity's understanding of the cosmos was forever transformed. This discovery represented more than just finding another planet. It was proof that the universe operates according to comprehensible mathematical laws, that through equations and models, humans could predict the existence of objects never before seen. Neptune's discovery was a triumph of intellect over the limitations of our senses, demonstrating that we could know about things beyond our direct perception. Recent historical analysis of ancient observations has revealed that Galileo Galilei may have unknowingly observed Neptune as early as 1612, when it happened to be near Jupiter, but he mistook it for a fixed star in his crude telescope. This near-miss discovery makes Neptune's mathematical prediction all the more remarkable. The planet had been hiding in plain sight, waiting for mathematics to reveal its existence. Can you imagine the moment of exhilaration when Galle confirmed Le Verrier's prediction? What other cosmic entities might be influencing our solar system that we haven't yet detected? And how might similar mathematical approaches help us discover worlds around other stars that telescopes can't directly observe? The Azure Guardian, why Neptune shines with an unearthly blue. When the Voyager 2 spacecraft captured the first detailed images of Neptune in 1989, humanity's first and so far only close-up look at this distant world, astronomers and the public alike were stunned by its vivid, almost unnatural blue coloration. This wasn't just any blue, but an electric, vibrant azure that seemed to glow against the blackness of space like a cosmic sapphire. The science behind Neptune's distinctive color reveals fascinating insights about its composition and atmosphere. Unlike Earth's oceans, which appear blue due to water-absorbing red wavelengths of sunlight, Neptune's color stems from something entirely different: methane gas. Neptune's atmosphere is composed primarily of hydrogen, 80%, and helium, 19%, but it's the small amount of methane gas, about 1.5%, that creates its signature blue appearance. Methane has a remarkable optical property. It absorbs red and infrared light while reflecting blue wavelengths back to space. As sunlight penetrates Neptune's cloudy atmosphere, methane molecules trap the red portion of the spectrum while allowing blue light to scatter and reflect back to our telescopes. This selective absorption process, known as Rayleigh scattering, the same phenomenon that makes Earth's sky blue, but much more intense, transforms Neptune into the most vibrantly blue object in our solar system. What's particularly astonishing about this coloration process is that it happens despite Neptune receiving almost no sunlight. At its orbital distance of approximately 4.5 billion kilometers from the Sun, Neptune receives only about 1/900th the sunlight that reaches Earth. The light illuminating Neptune is 900 times fainter than what we experience on a bright Earth day. Yet this faint sunlight is still sufficient to create its striking blue appearance when filtered through its unique atmosphere. Recent observations from ground-based telescopes and the Hubble Space Telescope have revealed that Neptune's color isn't static. The planet undergoes subtle seasonal variations in brightness and hue despite its 165-year orbit around the Sun. During Neptune's southern summer, which began in 2005, increased ultraviolet radiation from the Sun causes photochemical reactions in the upper atmosphere that produce hydrocarbon haze particles, subtly altering the planet's appearance. The blue canvas of Neptune isn't uniform either. White clouds of frozen methane ice crystals streak across its surface, creating a marbled appearance. These high-altitude clouds form in the colder regions of Neptune's upper atmosphere, where temperatures can plunge to negative 218 degrees Celsius, negative 360 degree Aries. These clouds stand out dramatically against the blue backdrop, providing crucial reference points for tracking the planet's phenomenal wind speeds. If you could float through Neptune's upper atmosphere in a specialized craft, what would the world look like through your viewport? Would the scattered blue light create an even more intense azure glow than Earth's sky? And what might the complex interaction of light, gas, and aerosols tell us about atmospheres on distant exoplanets where similar processes may be occurring? Cosmic Colossus, the true scale of Neptune's grandeur. To truly comprehend Neptune, we must first grapple with its extraordinary scale. A world of proportions that defy our everyday experience. With a diameter of approximately 49,244 kilometers, Neptune dwarfs our home planet, measuring nearly 4 times wider than Earth. If you were to line up Earths across Neptune's middle, you would need almost 4 complete planets to span its width. Size comparisons help illuminate Neptune's true proportions. If Earth were the size of a golf ball, Neptune would be as large as a basketball. This immense volume means that more than 57 Earths could fit inside Neptune's boundaries, a truly colossal world by terrestrial standards. Yet among the outer planets, Neptune is actually modest in size, ranking as the 4th largest planet after Jupiter, Saturn, and its near twin Uranus. Neptune's mass tells an even more impressive story about its composition. It contains approximately 17.1 times Earth's mass, packed into a volume 57 times greater. This gives Neptune an average density of about 1.64 grams per cubic centimeter, considerably less dense than Earth's 5.51 God centimeter, but significantly more dense than gas giants like Saturn, 0.69 deep centimeter. This higher density compared to the gas giants reveals that Neptune contains a much greater proportion of heavier elements, the ices, that give it its classification as an ice giant. Recent gravitational measurements and computer modeling have refined our understanding of Neptune's internal mass distribution. Unlike Jupiter and Saturn, which are composed predominantly of hydrogen and helium, approximately 80% of Neptune's mass consists of a hot, dense fluid of ices, water, methane, and ammonia mixed with rocks. This composition difference makes Neptune fundamentally different from both the terrestrial planets and the gas giants, representing a distinct planetary category. The term ice giant requires clarification, as it can be misleading. Despite the name, Neptune is not a frozen world. The ices in Neptune exist in a superheated fluid state due to the enormous pressures and temperatures in the planet's interior. At Neptune's core, temperatures may reach 7,000 degrees Celsius, 12,632 degrees, comparable to the surface of the Sun, while pressures soar to several million times Earth's atmospheric pressure, creating exotic states of matter unlike anything we experience on Earth. Neptune's size gives it substantial gravitational influence, allowing it to hold 14 known moons in orbit and maintain a system of faint rings. Its gravitational dominance extends far into the outer solar system, where it has shaped the orbits of countless objects in the Kuiper belt over billions of years. In fact, Neptune's gravitational influence was responsible for flinging Pluto into its current eccentric orbit approximately 3 billion years ago, according to recent computer simulations. Consider for a moment the sheer magnitude of Neptune, a world so vast that the distance across its diameter is nearly twice the distance from Earth to the Moon. How might living on a planet of such immense scale change our perspective on space and distance? And what engineering challenges would future explorers face when attempting to study a world where everything, from gravity to weather, operates on such an amplified scale? Supersonic tempests, the most violent weather in the solar system. If Earth's most powerful hurricanes leave you in awe, Neptune's weather systems would render you speechless. This distant world hosts the most extreme atmospheric conditions known in our solar system, with wind speeds that make our fiercest storms seem like gentle breezes by comparison. The winds of Neptune are truly extraordinary, reaching measured velocities of up to 2,100 kilometers per hour, speeds that exceed Mach 1.5 in Earth's atmosphere. These are the fastest planetary winds ever recorded in our solar system, over 5 times faster than the most powerful hurricanes on Earth. To put this in perspective, Neptune's winds travel faster than a high-powered rifle bullet and would cross the continental United States in under 2 hours. These supersonic gales tear around the planet, creating massive storm systems that continuously reshape Neptune's visible appearance. What makes these extreme winds even more remarkable is their energy source. Unlike Earth, where weather is primarily driven by solar heating, Neptune receives less than 1/900th the sunlight that Earth does, far too little to power such violent atmospheric movement through direct solar heating. Instead, scientists believe Neptune's weather is primarily driven by 2 alternative energy sources: internal heat radiating from the planet's core and the Coriolis effect created by the planet's rapid 16-hour rotation. Infrared measurements have revealed that Neptune radiates 2.61 times more energy than it receives from the Sun, the highest ratio of internal heat to absorbed solar energy of any planet in our solar system. This internal heat, left over from Neptune's formation 4.5 billion years ago, rises through convection currents that, when combined with the planet's rapid rotation, generate the extreme wind patterns observed in its atmosphere. Perhaps the most famous feature of Neptune's turbulent atmosphere was the Great Dark Spot, an Earth-sized anticyclonic storm observed by Voyager 2 in 1989. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's dark spots are transient features. When the Hubble Space Telescope looked for the Great Dark Spot 5 years after Voyager 2's flyby, it had completely disappeared, though new dark spots had formed elsewhere in the atmosphere. This indicates a much more dynamic and changeable weather system than those found on Jupiter or Saturn. Recent observations have revealed even more about Neptune's evolving weather patterns. The Hubble Space Telescope and ground-based observatories equipped with adaptive optics have tracked the formation and dissolution of multiple dark vortices between 2015 and 2022, including one that migrated across the planet's northern hemisphere before dramatically changing direction, a behavior never before observed in planetary atmospheres. These studies suggest that Neptune's storms may be linked to deeper atmospheric layers and potentially to processes occurring in the planet's interior. The temperature variations in Neptune's atmosphere are equally extreme. At the cloud tops, temperatures hover around -218 Celsius, -360°60°F, while just a few hundred kilometers deeper, temperatures rise dramatically due to increasing pressure. This sharp temperature gradient likely contributes to the planet's violent weather, creating thermal instabilities that feed into the storm systems. Picture yourself hovering above Neptune's clouds in a specially designed craft, watching as cloud systems race beneath you at speeds faster than sound itself, driven by energy sources completely different from those powering Earth's weather. What might atmospheric scientists learn about extreme weather dynamics by studying Neptune's storms? And could understanding the energy mechanisms behind Neptune's winds help us better predict and model climate systems on Earth and potentially habitable exoplanets? The Diamond Deluge, Neptune's bizarre interior world. Beneath Neptune's turbulent blue exterior lies one of the most exotic environments in our solar system, a realm of extreme pressures, scorching temperatures, and conditions so alien they transform familiar substances into states of matter that defy our everyday experience. While we cannot directly observe Neptune's interior, advanced computer models, laboratory experiments, and gravitational measurements have provided increasingly detailed glimpses into this hidden domain. Unlike the gas giants Jupiter and Saturn, Neptune's interior isn't dominated by metallic hydrogen. Instead, it hosts a progression of increasingly exotic phases of water, ammonia, and methane, substances astronomers collectively refer to as ices, though they exist nothing like ice as we know it on Earth. Under the crushing pressures and searing temperatures inside Neptune, these compounds form a superheated, electrically conductive fluid sometimes called a supersonic ocean. Recent high-pressure laboratory experiments at facilities like the National Ignition Facility and the Z-Pulse Power Facility have created Neptune-like conditions by compressing water to millions of times Earth's atmospheric pressure while heating it to thousands of degrees. Under these extreme conditions, water molecules break apart, with oxygen atoms arranging themselves into a crystalline lattice, while hydrogen atoms flow freely like a liquid, a state called supersonic water that behaves partly like a solid and partly like a liquid. These experiments confirmed theoretical predictions from the 1980s and revealed that much of Neptune's interior likely exists in this exotic state. Perhaps the most captivating prediction about Neptune's interior is the possibility of diamond precipitation. Computer simulations suggest that at depths of approximately 7,000 kilometers below Neptune's cloud tops, the extreme pressure and temperature conditions could cause methane molecules, CHA score, to decompose, releasing carbon atoms. These carbon atoms could then crystallize into diamond structures that would snow downward toward the planet's core. In 2017, scientists at the SLAC National Accelerator Laboratory successfully recreated Neptune-like conditions and observed this diamond formation process in real time, confirming that this seemingly fantastical phenomenon is theoretically possible. At Neptune's heart likely sits a solid core composed primarily of rock and ice, with a mass approximately 1.2 times that of Earth. The core temperature may reach about 7,000 degrees Celsius, 12,632 GeV, comparable to the surface of the Sun, while pressures could exceed 7 million times Earth's atmospheric pressure. These extreme conditions may create forms of rock and ice that exist nowhere else in our solar system, with crystal structures and properties unlike anything we've studied on Earth. Neptune's powerful magnetic field, roughly 27 times stronger than Earth's, provides additional clues about its interior. Unlike Earth's magnetic field, which is generated by molten iron in our outer core, Neptune's field is produced by the supersonic ocean, where free-flowing hydrogen ions can conduct electricity. Strangely, Neptune's magnetic field is tilted 47 degrees from its rotational axis and offset from the planet's center by nearly 10,000 kilometers, suggesting complex fluid dynamics in the planet's deep interior. According to research published in Nature Astronomy in 2020, these unusual magnetic properties may result from a thin, electrically conductive layer surrounding Neptune's core, possibly a concentrated brine of water, ammonia, and other compounds. This layer could act as a fluid electrical conductor, generating Neptune's offset magnetic field through a process similar to Earth's shear dynamo, but with fundamentally different materials. Try to envision the surreal landscape that might exist deep within Neptune, a realm where water exists as neither solid, liquid, nor gas, where diamond crystals fall like snowflakes through a dense, superheated ocean, and where familiar materials take on exotic forms under pressures millions of times greater than what we experience on Earth. What fundamental insights about matter itself might we gain by studying these extreme conditions? And how might understanding Neptune's interior help us identify potentially similar worlds among the thousands of exoplanets we're discovering around other stars? Triton, the captured world with backward orbit and nitrogen geysers. Among Neptune's 14 known moons, one stands out as particularly extraordinary. Triton, a world of superlatives and science fiction-like qualities. At 2,700 kilometers in diameter, this substantial moon is the seventh largest in the solar system, larger than Pluto, and nearly 80% the size of Earth's moon. Yet size is perhaps the least interesting thing about this enigmatic world. Triton has a profound secret written in its orbit. It circles Neptune in retrograde, moving in the opposite direction of Neptune's rotation. This backward motion is a smoking gun that Triton wasn't born alongside Neptune, but was captured from elsewhere in the solar system. According to the leading theory, Triton was once a large dweller of the Kuiper Belt, similar to Pluto, that ventured too close to Neptune billions of years ago and was gravitationally snared, forced into servitude as a moon of the ice giant. This capture scenario wasn't merely a gravitational handshake, it was a violent cosmic event. Recent computer simulations published in the Astrophysical Journal suggest that Triton's capture would have disrupted Neptune's original moon system, potentially destroying or ejecting several primordial moons. The energy dissipated during this capture would have initially placed Triton in a highly elliptical orbit that gradually circularized over millions of years through tidal interactions with Neptune. When Voyager 2 flew past Triton in 1989, it revealed a world unlike any other we've discovered. Triton's surface temperature of negative 235 degrees Celsius, negative 391 degrees, makes it the coldest known world in our solar system, even colder than Pluto. Despite this extreme cold, Voyager 2 observed something astonishing. Active nitrogen geysers erupting from the moon's southern polar region, shooting dark material up to 8 kilometers high into its tenuous atmosphere before depositing it downwind in dark streaks. These cryovolcanic eruptions make Triton one of only 4 bodies in our solar system where active eruptions have been directly observed, the others being Earth, Jupiter's moon Io, and Saturn's moon Enceladus. The mechanism behind these geysers appears to be sublimation. When nitrogen ice beneath a translucent surface layer absorbs sunlight, it heats slightly and transitions directly from solid to gas. The pressurized nitrogen gas eventually erupts through weak points in the surface, carrying dark particles with it. Triton's surface is a bizarre landscape of features found nowhere else in our solar system. The southern hemisphere contains what scientists call cantaloupe terrain, a strange network of intersecting ridges and depressions resembling the skin of a cantaloupe melon. This unique topography may result from diaparism, where blobs of less dense material rise through the denser ice crust, similar to how lava lamps operate but with ice of different compositions. Infrared spectroscopy has revealed that Triton's surface is composed primarily of nitrogen ice, with smaller amounts of water ice, carbon dioxide ice, and methane ice. The pink and rosy hues visible in enhanced color images come from tholins, complex organic compounds formed when methane is exposed to ultraviolet radiation. These same compounds are thought to give Pluto its reddish tint, further supporting Triton's origin as a Kuiper belt object. Triton's fate appears to be sealed by orbital mechanics. It's gradually spiraling inward toward Neptune due to tidal interactions, a mathematical certainty that will eventually bring it within Neptune's Roche limit, the distance at which a moon can be torn apart by tidal forces. In approximately 3.6 billion years, Triton will either be destroyed, forming a spectacular ring system around Neptune, potentially more impressive than Saturn's, or be torn into countless fragments that rain down on Neptune's clouds. Imagine standing on Triton's frozen nitrogen plains, watching spectacular geysers erupt against a sky dominated by Neptune, appearing 10 times larger than our moon does from Earth. What would it be like to explore a world where the sun appears as just a bright star, where nitrogen flows like water, and where you're walking on the surface of what was once a free-ranging planetoid? And what might Triton's active cryovolcanism tell us about the potential for similar activity and possibly subsurface oceans on other icy worlds throughout the outer solar system? Cosmic keystone. Neptune's role in solar system architecture. Neptune isn't merely an interesting world in isolation. It plays a pivotal role in the architecture and evolution of our entire solar system. This distant ice giant functions as a gravitational keystone, influencing countless objects in the outer solar system and providing crucial insights into planetary formation processes throughout the cosmos. Perhaps Neptune's most significant contribution to solar system dynamics is its relationship with the Kuiper belt, the vast region of icy bodies beyond Neptune's orbit. Much as Jupiter shepherds the asteroid belt, Neptune acts as the primary gravitational architect of the Kuiper belt structure. Through a process called orbital resonance, Neptune has organized many Kuiper belt objects, KBOs, into specific orbital patterns where they complete a precise number of orbits for every orbit Neptune makes. Pluto represents the most famous example of this Neptune-driven ordering, locked in a 2-to-3 resonance with Neptune, completing exactly 2 orbits for every 3 Neptune orbits. This resonance protects Pluto from close encounters with Neptune despite their crossing orbital paths. Astronomers have discovered hundreds of other objects sharing this same resonance, collectively called Plutinos. Other KBOS exist in 1-to-2, 2-to-5, and 3-to-5 resonances, creating a complex, Neptune-orchestrated gravitational dance at the solar system's edge. Neptune's influence extends even further. According to the widely accepted Nice model, named after Nice, France, where it was developed, a dramatic rearrangement of the outer planets occurred approximately 4.1 billion years ago, when Jupiter, Saturn, Uranus, and Neptune were in different orbits than they occupy today. During this period of instability, Neptune may have migrated outward by as much as 10 astronomical units, scattering billions of objects as it moved. This Neptune-driven reorganization likely created the scattered disk, a population of KBOS with highly elongated and inclined orbits, and may have been responsible for the late heavy bombardment, a period when the inner solar system was pummeled by an increased flux of asteroids and comets. Recent computer simulations published in Nature in 2022 suggest that Neptune's migration may have even influenced the delivery of water to the early Earth, contributing to the conditions that made life possible on our planet. Beyond our solar system, Neptune provides a crucial reference point for understanding exoplanets. Astronomers have discovered that Neptune-sized worlds are remarkably common around other stars, with NASA's Kepler mission revealing that approximately 25% of Sun-like stars host at least one Neptune-mass planet. These findings suggest that the processes that formed our Neptune may be a standard feature of planetary system formation throughout the galaxy. Neptune's interior composition, rich in water, methane, and ammonia, also offers clues about the solar system's formation environment. Based on isotopic ratios measured by the Voyager 2 spacecraft, scientists believe Neptune formed beyond the frost line in the early solar nebula, the distance from the young sun, where temperatures were cold enough for volatile compounds to condense into solid ice particles. The abundance of these ices in Neptune provides a direct link to the composition of the protoplanetary disk, from which our entire solar system formed. Consider Neptune's profound cosmic influence, how a single world has shaped billions of objects over billions of years, potentially influenced Earth's water supply, and provides a template for understanding countless similar planets throughout the universe. How might Neptune's continued study reshape our understanding of not just our solar system's history, but the fundamental processes that create planetary systems everywhere? And what might Neptune tell us about our own planet's place in this grand cosmic context? Frontiers of Exploration, the Future of Neptune Science. Despite being one of the most fascinating worlds in our solar system, Neptune remains one of the least explored. Since Voyager 2's brief flyby in 1989, the only spacecraft to ever visit the ice giant, our understanding has advanced primarily through Earth-based telescopes and the Hubble Space Telescope. However, the coming decades promise revolutionary new insights as next-generation observatories and potential dedicated missions prepare to unlock Neptune's remaining secrets. The James Webb Space Telescope, JWST, represents our most powerful new tool for studying Neptune. Its advanced infrared capabilities can penetrate Neptune's upper atmosphere, revealing temperature distributions, weather patterns, and atmospheric composition with unprecedented detail. Early JWST observations in 2022 captured stunning images of Neptune's rings with clarity never before achieved from Earth orbit and detected previously unknown weak bands in Neptune's atmosphere. As JWST continues its mission, regular monitoring of Neptune will reveal seasonal changes and dynamic weather patterns, potentially connecting surface features to deeper atmospheric processes. Ground-based astronomy continues to advance our understanding as well. The Extremely Large Telescope, ELT, currently under construction in Chile with a primary mirror 39 meters in diameter, will provide Neptune images with resolution approaching what Voyager 2 achieved from much closer range. Combined with adaptive optics technology that compensates for Earth's atmospheric distortion, the OLT will track Neptune's evolving storm systems and cloud patterns with extraordinary detail beginning in the late 2020s. The planetary science community has long advocated for a dedicated Neptune mission, a true orbital reconnaissance rather than another brief flyby. In NASA's 2023 to 2032 Planetary Science Decadal Survey, an ice giant mission was identified as the highest priority flagship mission, recognizing the significant knowledge gap regarding Uranus and Neptune. The proposed Neptune Odyssey mission concept would include an atmospheric probe to directly sample Neptune's cloud layers and an orbiter to study the planet's interior, magnetic field, rings, and moons over several years. Such a mission would face significant challenges. Neptune's immense distance means a spacecraft would require 8 to 12 years to reach it, using conventional propulsion systems. The minimal sunlight available at Neptune's orbit makes solar power impractical, necessitating radioisotope thermoelectric generators, RTGS, for electrical power. Despite these hurdles, recent advancements in ion propulsion, air capture techniques, and spacecraft miniaturization have made a Neptune orbiter more feasible than ever before. The scientific payoff would be immense. Direct sampling of Neptune's atmosphere would reveal its precise composition, helping resolve debates about the planet's formation. Repeated gravity measurements would map Neptune's internal mass distribution with unprecedented accuracy. Magnetometer readings would reveal the dynamics of Neptune's unusual magnetic field, potentially providing insights into the planet's interior structure. High-resolution imaging would track Neptune's evolving weather patterns over years rather than days. Perhaps most excitingly, close-up study of Triton would be a mission highlight. With its nitrogen geysers, unique surface features, and potential subsurface ocean, Triton ranks among the most promising targets for astrobiology in the outer solar system. The 2023 Decadal Survey specifically noted that a Neptune-Triton mission could address both ice giant science and ocean world objectives, potentially revealing whether this captured Kuiper Belt object harbors the ingredients for life. Beyond direct exploration, Neptune continues to benefit from advances in theoretical modeling. Increasingly sophisticated computer simulations are helping scientists understand Neptune's interior dynamics, magnetic field generation, and historical migration. Laboratory experiments recreating Neptune-like pressures and temperatures are revealing new insights about exotic states of matter that may exist within the planet. The synergy between these theoretical approaches and observational data will drive Neptune science forward even before a dedicated mission arrives. What revolutionary discoveries might await when we finally dispatch a dedicated orbiter to this distant blue world? How might a comprehensive study of Neptune and Triton transform our understanding of ice giants, Kuiper Belt objects, and potentially habitable worlds? And what technological innovations might emerge from the challenge of exploring such a remote and extreme environment? Beyond the blue horizon, Neptune's enduring mysteries. As our journey to Neptune concludes, we're left with a profound appreciation for this distant ice giant, a world that challenges our understanding of planetary physics, reveals exotic states of matter, and may hold keys to comprehending thousands of similar worlds throughout our galaxy. From its mathematical discovery that revolutionized astronomy to its extreme weather systems and mysterious interior, Neptune exemplifies the wonders awaiting exploration at the solar system's frontier. Neptune's importance extends far beyond scientific curiosity. As one of only 2 ice giants in our solar system, it represents a crucial data point in understanding planetary diversity. Recent exoplanet surveys have revealed that Neptune-sized worlds may be among the most common planets in our galaxy, making our Neptune a vital reference for interpreting these distant discoveries. By studying the one ice giant we can observe up close, scientists gain insights into a whole category of worlds that appear abundant throughout the cosmos. Despite all we've learned, Neptune remains shrouded in mystery. We still don't fully understand the mechanisms driving its extreme winds, or why its magnetic field is so dramatically tilted and offset. The precise composition of its deep interior, the potential existence of diamond precipitation, and the dynamics of its unusual moon system all present unresolved questions. Each answer we uncover about Neptune seems to generate new questions that challenge our existing models and push the boundaries of planetary science. The blue giant's influence on our solar system's history continues to be reassessed. Recent simulations suggest Neptune may have formed much closer to the Sun before migrating outward, reshaping the outer solar system as it moved. This migratory history may have influenced the delivery of volatile materials to the inner planets, potentially including the water that makes Earth habitable. Neptune thus becomes not merely a distant curiosity, but a key player in the processes that made our own existence possible. As technology advances and our reach extends further into space, Neptune beckons as a destination rich with discovery potential. The ice giant's extreme environments offer natural laboratories for studying physics under conditions impossible to recreate on Earth. Its bizarre internal structure provides insights into exotic states of matter. Its active moon Triton presents one of the solar system's most compelling astrobiological targets. Neptune truly represents a frontier of human knowledge, a distant world waiting to reveal secrets that could transform our understanding of planets throughout the cosmos. Perhaps what makes Neptune most compelling is how it challenges our place in the universe. This distant blue world reminds us that our solar system extends far beyond the familiar planets visible to the naked eye. As we gaze at Neptune, whether through powerful telescopes or spectacular spacecraft images, we're confronted with the immensity of space and the diversity of worlds it contains. Neptune stands as a cosmic horizon, marking not an endpoint but a gateway to the vast, largely unexplored outer regions of our solar system and the countless ice giants orbiting other stars. Thank you for joining me on this exploration of Neptune, the mysterious ice giant at the edge of our planetary family. As you continue your own cosmic journey of discovery, remember that even this distant blue world, requiring the most powerful instruments to study, was ultimately revealed through human curiosity, ingenuity, and our relentless drive to understand the universe we inhabit. Until our next voyage into the cosmic unknown, keep looking upward and outward. For there, in the depths of space, wonders like Neptune await those bold enough to seek them.